Good afternoon.
Good afternoon.
Good afternoon, sir.
Good
Good
afternoon,
afternoon,
sir.
sir.
Good afternoon.
Sir.
Yesterday I shared a link.
Their voice is not audible.
Uh, Yesterday I shared link on WhatsApp group. Join team for algebra. Right. So all of you saw the link.
Sir, actually, your voice
Yes,
is
sir.
very.
Okay. Is it audible now?
Oh, yes, sir. Yes, sir.
So
Yes, sir.
yes. So
Sir, actually, I want to join the WhatsApp group. So, can you share your link?
actually I am not admin of that group. Somebody can add you or okay. I will try to share the link. No problem.
Okay, sir. Thank you.
Anyway.
Sir, I still did not get my MS ID.
You will get it later on, don't worry, because
Okay.
IDs are distributed in batches, so you will get it later. Don't worry. Okay, so yesterday we were talking about natural numbers, right? And we wanted to understand the properties of natural numbers and from that induction. Right, so where we were last time, so we were talking about rational numbers and what are the rational numbers, what was the how rational numbers are came in picture, because people thought that key integers are sufficient, but then came across some equations whose solution is not available in integers. For example, 2x plus 3. So can you see my screen?
Yes, sir.
Yes,
Yes,
sir.
Yes,
sir.
sir.
Yes,
Yes,
sir.
sir.
Okay,
Yes, sir.
so you can see whiteboard. Yes, can you see my board, whiteboard?
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
okay, fine. Okay, so the equations like 2x plus 3 do not have solution in integers, and therefore it was a need to improve our system, number system. And then people introduced the new numbers p by q type. P and q are integers and q is non-zero. Right, so such numbers were included in the number system, and that set becomes a more larger set, right? And that set is called as set of rational numbers. Right, so set of rational numbers is the elements of the type p by q. So set of rational numbers that we introduced last time. So it is denoted by this special symbol. And what are the elements of this set? P upon Q, where P and Q are integers, right? So as we saw last time, this is a notation for set of integers where and Q is non-zero, right? So if Q is zero, then it doesn't make sense. So all such type of elements are rationals or rational numbers. And uh, actually, what are the rational numbers, or how to visualize these numbers, or how to understand where do we use such numbers? So, for example, as we saw last time, what is a 2 by 3? So 2 by 3 is a number, or 1 by 3 is a number. So you divide one unit, whatever is, you have one bread, or you have one unit length, or whatever you have, divide it into 3 equal parts, and one part is 1 by 3, and two parts together is 2 by 3, and so on. And in the same way, what is 1 by 100 and what is 5 by 100? So similarly you can understand this, right? So this is a set of rational numbers. But again, people thought that okay, this is sufficient, our set is now big enough and we don't need more numbers. That was the people were thinking at that time, right? and they saw that they believed that this is sufficient. We don't need more numbers, right? But then people were thinking that if you fill this line by rational numbers, right, then you can completely fill up this line. People were thinking this. If you can put if you put all the rational numbers on line, then line will be completely filled by rational numbers. But then later on, what happened? Some mathematician showed that suppose I have a right angle triangle whose sides are of length 1 and 1. Then what is this length? Right? What is the length of hypotenuse? So what is the length of hypotenuse?
Root 2.
Root 2, right? And then
Root 2.
so then what is this length? People thought that if all numbers are known and no need to find more numbers, then what is this length? And then this length, is it rational number? People were thinking about it, and then some mathematician then they found that so prove that root 2 is not a rational number. Right, so root 2 is not a rational number. Okay, let us prove this. And then once we prove this, then we believe that the length of hypotenuse is not in rationals. And then people feel that okay, we need to add more numbers because there are more numbers which are useful. Right. So suppose we want to prove that root 2 is not rational number. So let us assume that
Root 2 is a rational number.
assume that root 2 is rational. Right. Suppose root 2 is a rational number. Then what will happen? But
Root 2
then,
can be written in the form of P by Q.
then we can write root 2 in the form of P by Q, where P, Q are integers. Q is not equal to
Not
0.
equals to 0.
And GCD of P and Q is 1. Least form. That is least form. We assume.
The screen is not visible.
Can you?
happening in between.
Okay, it might be happening due to internet connectivity, so that may happen. But is it visible now?
Yes, sir.
Yes, sir.
Yeah. Yeah.
Yes, sir.
Okay. So, rational number, suppose root 2 is a rational number, it is in the type P by Q, and assume that it is in list form. List form means, for example, if you look at 1 by 2 and 2 by 4, the value is same, and therefore we can uh, neglect the common factors. So we can cancel 2. We can neglect common factors. So in the list form, suppose we assume root 2 is a rational number and it is P by Q. If at all there are common factors, cancel them out, and it is now in list form. Right. So squaring this, what we get, if we square this equation, 2 is equal to P square
P
upon
square, Q square.
right, and therefore 2Q square is same as P square.
P square.
Now in this expression, so let us
2
call
is
this
the
as
factor of P.
so 2 divides LHS, right? 2 divides LHS because 2 is a factor of LHS, and therefore 2 must divide RHS because LHS and RHS are equal. So 2 divide
Sir,
RHS.
your screen is not visible.
It might be happening due
So,
to internet.
so actually, when you're writing, it's becoming blank, and when you're not writing, it's clear.
Yeah, so there is a lag, right, in my writing and whatever you see. Okay, Can you see
Okay.
now?
Yes, sir.
Okay, so let me repeat it again. So 2 is a factor of left hand side. So left hand side is same as right hand side, and therefore 2 is a factor of RHS, right? And so
Yes.
that 2 divide p square, right? But now 2 is a prime number. Okay, we are yet right now we assume what is your previous knowledge about prime number. We don't know what is p. P is some number, integer, but 2 is a prime number, and if some prime number divides square of some number, then 2 divides p. Right? If 2 divides p square, then 2 must divide p. Right? So that you can check by for particular cases, but it is true, and that will prove later on. Right now just assume that if p divides 2 divides some square of some number, then 2 must divide that number p itself. And so since 2 divides p means what does it mean? So
P is
2
even
is a factor of p.
okay, so 2 is a factor of p. So 2 is a factor of p, therefore p is, what is p is 2 times k for some integer k, right? That is what we are interested in. So therefore from expression 1, so from expression 1, 2q square is equal to p square, but p square is 2k, p is 2k, so it is 2 square k square, right? That means
4k
2q
square.
square is equal to 4 times k square, but we can cancel 2 because multiplicity inverse of 2 exists, and
Now
hence
2 is a factor of q.
q square is equal to 2 times k square, and hence 2 divides
Q.
q square, and hence 2 divides q. Right, so why 2 divides q square? Because 2 divides RHS, right? 2 divides RHS. Let us call this as expression 2. So 2 divides RHS of expression 2, and therefore 2 divides LHS, right? And 2 divides LHS, therefore 2 divides q square, and therefore 2 divides q. So ultimately what we get, thus 2 divides q and 2 divides p, right? And therefore what will be GCD of p and q? That means definitely q is a common factor of p and q. So definitely 2 is a common factor of p and q. Therefore GCD, greatest common divisor of p and q, is at least 2, right? Because at least 2 is a common factor. Is it clear? Right, because at least 2 is there. There might be many more common factors, we don't know, but from this we are sure that 2 is a common factor, and therefore GCD, if it is GCD, then it must be greater than or equal to 2, or it may be more than 2 or equal to 2. So what is a contradiction? So this is a contradiction to, this is contradiction to the assumption, right? So what was our assumption? That GCD of
2 is
P
not
and Q is 1, right? Because in the beginning we assume that whatever is common among P and Q, cancel it out, and we assume that P by Q is in list form. That was our initial process, initial starting point, right? And we started within list form. That means there was no common factor at all among P and Q. But at the end, what we found, at least 2 is a common factor, or there are more common factors. That is a contradiction. Hence, And what leads us to the contradiction? What leads us to the contradiction? Therefore,
is not rational number.
Rational number.
right, because we assume that root 2 is a rational number, and that leads us to contradiction. Therefore, root 2 is not a rational number. Right. So root 2 is not a rational number. Now we are sure about that root 2 is not a rational number. But what is the hypotenuse of this right angle triangle whose sides are 1? Right. So hypotenuse is root 2 and it is not available in our number system. So people thought that we should improve our number system. There are many such numbers which are not there in the rationals, and therefore the new numbers are called as complement of rationals or irrational numbers. Irrational numbers. Such numbers are called as irrational numbers, and therefore what is a set of real numbers? So real numbers is denoted by this notation, and it is rationals together with irrationals. So this is a set of real numbers. Now people came across various equations like x square minus 2 is equal to 0. So this equation do not have solution in rational, so that means there must be numbers. So this is another approach, right? So in real calculus 1, you will study another aspect of irrationals by Richard Dedekind, Dedekind cuts. There are cuts on line and those cuts are called as irrational numbers. So that is a different aspect anyway. But right now we are just interested in number system and natural numbers, right? And later on, if you go in history, so still people thought that okay, real numbers are sufficient for us. But while doing many calculations, people came across equations like this: x square plus 1 is equal to 0. Right. So this equation do not have a solution in real numbers. Right. So this equation do not have a solution. Suppose x is a solution, then x square will be minus 1. But what is the very important property of real numbers? Key square of every real number
Is always positive.
always positive. Is positive. Right. This is the important property of real numbers. And if x is a real number, then its square would be negative, which is not possible, right? And therefore, there is no real number at all, which is a solution of this equation. And therefore, people improved the system, number system, that is complex numbers. But as far as our course is concerned, we are not very interested in complex numbers right now. Later on, we'll discuss about complex numbers, right? Okay, so let us come back to natural numbers because our main aim is to see the inductive property of natural numbers and induction. So okay, let me tell you that we first saw natural numbers, then whole numbers, right? Then we saw bigger set integers. Then we saw that bigger than that rationals, and from that real numbers, right? And these are the proper subsets, not equal. Proper subsets, not equal. So in this way, and set of complex number is the largest set you can say, which includes imaginary numbers. So numbers which are not real are called as imaginary number. For example, what is x whose square is minus 1? So it cannot be real number, and therefore in this case x is square root of minus 1, which is denoted by I. I stands for imaginary number, right? And then you can identify complex number as a points in plane and so on. That we'll discuss about these complex numbers in detail later on. Okay, so this is fine. Now this is our number system, and in calculus you will study the detailed property of real numbers, and ultimately that will include properties of rationals and all other things, right? And at some point of time in algebra, we'll discuss many more properties of integers also, right? And therefore, as far as algebra is concerned, we are interested in natural numbers and integers, right? Okay, so inductive properties of natural numbers. So inductive property of natural numbers. So inductive property has different versions, right? So what are these versions? So first basic version, so first, or you can say its version or avatar 1. What is the first version? 1 is a natural number. 1 is a natural number, and if n is a natural, or you choose any number from set of natural numbers, then n plus 1 is also natural number, right? So this is what the basic property of natural numbers. So inductive property, if you choose basically 1 is initial natural number is 1, and if you choose any number from set of natural numbers and add 1 in it, next number, the next number is in it. So that this shows that there are infinitely many natural numbers, right? So what is another version is second avatar of inductive property. So let S is a subset of natural numbers. Suppose S is a subset of natural numbers. Suppose if S satisfies the following properties. So S satisfies following properties. What properties S satisfies? One is in S, and second property, if you choose any element from S, then k plus 1, if you choose any element k from S, then the next number is also in S. Then S is nothing but set of natural numbers. So if you choose any subset of natural numbers, and if it includes 1, and if you choose any number from that element set S, then the next element, if you add 1, the next element is also member of S, then that set is nothing but exactly the set of natural numbers, right? So this is more general definition of natural numbers in some sense, because any set having these properties, any set having these properties is called as set of natural numbers, right? So any set having these properties means what? Suppose you have some sets, whatever objects in that set may be, as I told you last time, yesterday's lecture, uh, these symbols 1, 2, 3 that we use for natural numbers are not special at all. For our understanding, we have accepted it and we are using it, and therefore the members are just numbers. And you can in real life situation, you can have set of objects, and suppose you assign one object as a first object, and you assign second object is a consecutive next object, and so on. And in this way, if you have infinitely many objects, then that is a set of natural numbers, right? But for mathematics calculations, we are considering natural numbers as an abstract set, right? But in real life situation also such situation occurs. Anyway, so this is a one avatar of natural numbers. Okay, now then what is Next, as a application of this inductive property, right? So mathematical induction. Or first uh, first form of induction, or sometimes it is also called as weak form of induction, or weak principle. These are different words used for same thing, weak induction. And how this weak induction is useful for us in mathematics. So weak induction is useful in mathematics to prove some mathematical results from mathematics, which we cannot, which are easy if you use apply induction. And induction is useful because inductive properties of natural numbers. So how induction works? So suppose Pn is a statement about natural numbers, right? So Pn is a statement about natural numbers. So it is a statement about natural numbers means what? So that is uh, the statement Pn is true for n in natural numbers. So it is about natural numbers, means the statement is defined for natural numbers. Now for example, statement about natural numbers means what? For example, uh, suppose what my statement could be, for each n, 2n plus 1 is an odd number, right? So this is a statement about natural numbers, right? Because for every natural number 2n plus 1 is odd number, right? So this is one kind of statement. You can have another statement key. For example, my statement Pn about natural numbers is the sum of first n natural numbers is the sum of first n natural numbers is the sum of first n natural numbers is, what is the sum of first n natural numbers? N into n plus 1 divided by 2, and you have already used it somewhere at some point of time, right? So that is, or 1 plus 2 plus 3 plus up to n. This is n into n plus 1 divided by 2 for each n in natural numbers. So if you take n is equal to 10, then the same formula is true. Suppose n is equal to 10, 10 into 10 plus 1, 11 divided by 2. So that is the sum of 10 natural numbers. What is the sum of 50 natural numbers? What is the sum of 100 natural numbers? So that is possible for any natural numbers. You take any number of first natural numbers at a time, and finitely many at a time, not infinitely many. Because if you take all the natural numbers at a time, or if somebody says if I choose even natural numbers at a time and all, that is not defined, or that is infinite. So that you will learn at the when you study sequences and series of numbers. Anyway, so these are the such kind of statements, PN, statement about natural numbers. Okay, so this is for example, right? This is not we were talking about. So we are talking about, suppose Pn is a statement about natural numbers. Then what is first statement? Step 1. Step 1 of induction. So prove that if Pn is true for n is equal to 1, or that is P1 is true. So this you need to prove, right? This we first of all we should verify or prove for n is equal to 1. For n is equal to 1, the corresponding statement Pn is true. Then what is the second step? So this is called as a basic step or base step. Right? So base step. Now, so next step, step 2. So is called as induction hypothesis. So this is called as induction hypothesis. That assume that Pk is true for k, for some k greater than 1. Right? This is assumption. What is the meaning of hypothesis? When we talk about theorems and their proofs, then we'll be using word like hypothesis. Hypothesis means assumption. Right. Assumptions means what? Suppose we have some data or initial knowledge, and from that knowledge we are going to prove some claim. Right. That is a conclusion. But whatever data available or assumption is, assume that Pk is true. This we are assuming. This is not proving, right? Assume that Pk is true for k. What k? So choose any k, and it is not convenient to choose k is equal to 2, 3, 4, and not convenient to take every k. So in general, suppose it is true for, or assume that it is true for some k greater than 1, and then what is the step 3? Inductive step. So what is the inductive step? Prove that the statement Pk plus 1 is true, or that is the result is true for n is equal to k plus 1. That is prove. That is prove that, not assumption. This is not assumption. So that is prove that the result is true for n is equal to k plus 1. So these are the steps. Okay, now try to understand these steps logically, because always there is a confusion. What is the first step? We have to prove for n is equal to 1. No way. We have to prove. And assume that here in second step we are not proving. We are assuming that this statement is true for n is equal to k, or for kth number it is true. And from that, using let me add here, using step 2, using step 2 prove that statement Pk plus 1 is true. That is using induction hypothesis, prove that result is true for n is equal to k plus 1. Then what is the conclusion? Then the statement Pn is true for all natural numbers. Now there must be there is a natural question in your mind ki how we can declare from these three steps ki it is true for all n, right? So because we are proving for n is equal to 1, that means the no doubt about first step we are actually proving ki for n is equal to 1 it is true. Now we are assuming a second step, that means suppose from kth step to k plus 1 it happens to be true. With same logic from 1 to 2 it will be true, right? From 2 to 3 it will be true because we have proved from k to k plus 1 it happens to be true. So with same logic from 1 to 1 to next, that is 2, it is true. From 2 to 3 it will be true. From 3 to 4 it will be true. And if we continue this, it will be true for all natural numbers, right? And then we can conclude this is true for all natural numbers. And why this conclusion is possible? This conclusion is possible because of the logic of this inductive steps, or these three steps works because of this inductive properties of natural numbers. Okay, again there could be a natural question in your mind, who defined these inductive properties? How do we get these inductive properties? Okay, so let me tell you that how these inductive properties came here, or who gave these inductive properties. So that is because of the in calculus 1 you will study the various properties of real numbers, and people wanted to have a set which is a nice set and which is useful in our day-to-day life. In that process people constructed set of real numbers, and set of real numbers contains natural numbers, and therefore while constructing the set of real numbers, these properties already people defined there, right? Defined means what? These are the building blocks of our number system. Building blocks means what? Suppose you took admission to the college, and what was in your mind? Okay, if I take admission to the college, then definitely there are classrooms, there are teachers, and so on. Many things are there. There are benches, there are tables, there are chairs, there is a library. That is your assumption, because these are building blocks of college or any institute. Or you construct house, then there is a window, there is a door, there are cupboards, and so many things are there, right? So these
Dining
are
tables.
pardon. So these are building blocks, and therefore while constructing number system, these properties, inductive properties or other properties which we'll be studying in future in this calculus course or algebra course, all these properties people define, and such properties are called as axioms, right? Axioms. So uh, axioms. So these are axioms, and these axioms are the main basic building blocks of particular system, number system. Without axiom, this system will collapse, right? And due to our requirement of number system, or requirement of real number system, these properties are there, and that's why the inductive properties are natural numbers, right? And because inductive properties are there, this induction works. Induction is useful for us, or mathematical induction works. Okay, so and therefore if you want to prove some statement is true, for statement about natural numbers is true, then what we need to follow? We need to follow these three steps, right? What are these three steps? First, prove for n is equal to 1 and assume for k, and from that prove for k plus 1. If it happens to be true from k to k plus 1, then we can definitely declare that कि our statement is true for all natural numbers. Okay, so
Excuse me, sir.
yes,
Sir, I think in step 2, k should be greater than or equal to 1, not greater than 1.
that you can say, because already for a k is equal to 1 we have proved, and then no harm in saying greater or equal 1, right? So that is fine. Okay.
Okay, sir.
Okay, so now let us say see simple examples, and then we'll go to some non-trivial example. So prove that 1 plus 2 plus 3 plus n is n into n plus 1 by 2 for all n in n. Right, so prove that sum of first n natural numbers is n into n plus 1 divided by 2. Right, and then follow the steps for induction. So what is the first step? Right, so prove for n is equal to 1. Try to prove for n is equal to 1. So if n is equal to 1, for n is equal to 1, what is LHS? What is LHS if n is equal to 1? Because our statement is this, right? This our whole statement is, right? This is our Pn, and what is LHS of Pn for n is equal to 1? 1, right? Very good. So for n is equal to 1, our statement LHS is 1. And what is RHS?
It will be also 1. 2 upon 2 is equal to 1.
Right. 1 into 1 plus 1 divided by 2. So it is 1. And therefore, LHS is equal to RHS. Thus, statement is true for n is equal to 1. Right, so we are done with first step. Then second step. So induction hypothesis. Right, so induction hypothesis. So what is induction hypothesis? Assume that the statement is true for n is equal to k, and k is some number greater than or equal to, but already we have proved for n is equal to 1, right? So somebody have kept mic on, so that's why there is a noise, I think. Okay. So what is induction hypothesis? Assume that statement is true for n is equal to k. So that means that is 1 plus 2 plus 3 plus k is equal to k into k plus 1 divided by 2. Right, this is our assumption now. This is not at all proof, right? And we cannot say that this is true. This we are assuming. And this will be true if we can prove third step, right? So assume that it is true for n is equal to k. Now what is next step? Inductive step. Step 3. Prove that the statement is true for n is equal to k plus 1. This we want to prove. This is assumption. Second step is assumption. Now third step we need to prove using, right? So we want to prove for n is equal to k plus 1 using induction hypothesis. right? So this is what we want. Okay, so that is what we want. What we want to prove. So we want to prove that key 1 plus 2 plus 3 plus up to k plus k plus 1 next, right? And what is it should be? What is what we expect our result to be? What we expect here?
K into K plus 1 by 2.
K plus 1, k plus 2 divided by 2. This we expect, right? Now let us check that we can prove our expectations, right? We are able to prove the expected answer, then we are done, and then we can declare that the result is true. So let us start with sum of k plus 1 numbers. Let us start with sum of k plus 1 numbers, right? And at the end we should get this answer. At the end we should be able to get this. If we are if we could, then we are done, and we'll declare that key result is true for k plus 1. And now, but this part is our assumption up to k, 1 2 3 up to k. That is our assumption by induction. This is assumption. That means we are assuming that this is true. This we are assuming, and therefore what is 1 plus 2 plus up to k is
K into K.
plus 1
K into K plus 1 upon 2.
plus the new number k plus 1, right? So very good. So k into k plus 1 plus, now simplify this, right, and whole divided by 2, and therefore it will be, so k plus 1 is a common in the numerator, and so I can write it as k plus 1 multiplied by k plus 2 divided by 2, and this is what we were expecting. See this?
Yes, sir.
Right, and hence thus the result is true for is true for n is equal to k plus 1, and by induction hypothesis, inductive steps or induction principle, what we can declare, hence the statement is true for n is equal to is true for each n, each natural number, right? So in this problem the steps were very easy, but the main point is you need to understand logically what steps we have to follow and how it works. That was the main point. Otherwise the calculations are very elementary calculations. So is it clear?
Yes, sir.
Yes,
Okay.
Yes, sir.
Okay,
Yes,
now
sir.
we are now interested in some non-trivial examples. These examples also in some sense very trivial, right?
Sir,
We are, yes.
sir, I have a doubt in Avatar 2. Sir, can you please explain that property with the help of example?
Yeah, so this is a kind of axiom. Axiom means is the basic setup of natural numbers. What it says, this is, you need to understand it in abstract manner. You choose any subset of natural numbers, and suppose it contains first natural number, and if you choose any element from that set S and add 1, the next number is also in S, then what is set S? Then set S itself is equal to set of natural numbers. It is not smaller set,
Okay, sir.
right? That is what the meaning of this. So ultimately at some point of time you can prove that these two are equivalent, these two avatars are equivalent. Right, there is one more avatar or version of this inductive property, right? So that is avatar 3, whatever it is. So well ordering property. Well ordering property of natural numbers, right? So well ordering property of natural numbers is equivalent to the previous two avatars of natural number, the inductive properties, right? And how to prove it? So that is again not difficult. You just find any set theory book and you see the proof, or if time permits in some practical sessions or otherwise we will try to discuss this also, because as far as our course is concerned we are not supposed to discuss this, but as a our part of it is related to our syllabus, so at some point of time we'll try to discuss it, right? But anyway, what is well ordering property? So before that, let me introduce some basic idea. Suppose I take set A, 1, 2, 3, 4. So what is a least element? Least
One.
element A
One.
is 1, right? And therefore, can you tell me the definition of least element? Okay, this is example 1. Now let me give you one more example. Example 2. What is my set A? All real numbers. Okay, I am taking real numbers now. Real numbers which are greater than 0 and less than 1. Right, so all numbers from 0 to 1, and therefore this set A does not include 0, right? 0 is not member. All numbers in this set A, second example, are strictly greater than 0 and strictly less than 1. So this set does not include 0 and 1, but everything in between is included. Is it clear?
Yes.
Yes, sir.
Yes.
Ah, now what is least element of this set? Second example.
0.1.
0.
But 0 is
Zero
not
point
the member. See, for example, see what is the least element. So, suppose you are in a class and somebody came and tell me the name of student who has least marks in mathematics, who have obtained least marks. So least marks means what? That student must be a member of class and he
Sir,
have
there are so many numbers.
no. So this set has no least element.
There is so number, sir. We can't define it. List number.
This set has no list element, right? Because, and this set has a list element, first example, why? And look at the definition. So let A is a non-empty set, right? A is a subset of real numbers, because basically we are talking about in general sense. So you should talk about set of real numbers. A is a non-empty subset of real numbers. An element alpha is the least element of A if alpha is a member of A, alpha must be member of A, and alpha is less than or equal to X for all other members of A. Right? So if at all list element exists, it must be a member of set, and all other members are either greater or equal to the list element. And what I said here, the list element, the list element. So list element, if at all exists, it is unique. That you should prove, right? So list element, if at all exists, it is unique. So this is what the definition of list element. And if you look at interval 0, 1, 0 is not included. In that case, no number is there in the set which is a list element. Somebody will say, okay, this is a list element, then I can find a smaller element in the set than that. You choose any element in the set, there are still smaller element than that, right? And 0 cannot be list element because 0 is not a member of set. Once you understand this definition of list element, then you can understand the well ordering property. And next time we'll see well ordering properties, because now it is 2 o'clock and you have to join next class, right? Any doubt?
Sir, attendance.
Yeah, I have taken attendance. I have downloaded it.
Okay, sir.
Thank you, sir.
Sir,
Yes.
sir.
Thank you.
Yes.
So do we have any WhatsApp group for it?
Yes, there is a WhatsApp group, right? Acharya sir created a WhatsApp group and you can join that.
Sir, I'm
Sir,
not
yes, sir.
WhatsApp group. How can I join that WhatsApp group?
Okay, I will tell Acharya sir to share the link so that you can join, right?
Sir,
Where I will get the
Yes.
link?
sir, I had a doubt.
Yes.
Sir, as we have earlier proved that root 2 is an irrational number, but
Yes.
further if we evaluate root 2, then it is 1.414. So it is a
No.
rational number, right?
No, it is not. That is approximation. 1.14, whatever you are saying, it is approximation. It is not exact value,
Okay, sir.
right?
Yes, sir.
For example, pi. Many times people say it is 22/7, but it is approximation of value of pi. It is not exact value. Remember this,
Okay, sir.
right? And this
Sir,
approximation, you can understand these approximations while studying series replacement theories in calculus.
Yes,
Sir,
sir.
can we leave?
Yeah. Okay.
sir,
Your- Yes.
Sir, how does the attendance
sir,
take
what
place?
See, if you are seeing my screen, can you see my screen?
Yes, sir.
Can you see here my cursor? Download attendance list.
No, sir, I'm not able to see
No,
that.
sir.
Do you see my screen? Black screen.
No, sir. The previous screen is visible, sir, where you were teaching.
Let see. I will share it again and then see what happens. Okay. Now can you see my screen? Can you see the screen?
Yes, sir. Yes, sir.
Here is a download attendance list, so I can download attendance from this immediately. Therefore, you should not worry about attendance,
Okay, sir.
right? So I have
sir,
Yes, sir.
downloaded.
what, sir, what you taught, we have to write in a book, or what we will get notes?
No, you should write down it in your notebook, and I will try to make a PDF of this written material also. But at the
Sir,
time of lecture,
because sir, I had not idea about that classes, so this is my first day to join these classes.
don't worry. You try to write down whatever we are discussing. That will be helpful for your future study.
Okay, sir.
Sir, can you?
I am not included in that WhatsApp group, so please add me in that WhatsApp.
You join my Google class. I will share